all to medical and sustainable technologies. How a nanotech toolbox can revolutionize medicine and energy storage. Jacky, Ying, Institute of Bioengineering and Nanotechnology, Singapore.
When the Berlin Wall came down, I was in Princeton doing my PhD thesis. I went to Germany as Alexander von Humboldt Research Fellow 2 years later.
Good morning. It's a great pleasure to be here 24 years after my postdoc in Germany through the Alexander von Humboldt Foundation's fellowship. I'm delighted to be able to share with you how the nanoscience has become really a technological toolbox to enable us to make major breakthrough in energy storage and various different medical technologies. First, let me start by a quick example of energy storage. As all of you know, the key here is that we need to have materials that has very high power density so that it allows you to use it and discharge very quickly. Now, the good recyclability basically ensures that the battery has a long life. So typically, when we try to use a battery, the electrons and the lithium are flowing from the anode to the cathode. And the reverse is happening when you're charging the battery. Now, many of us are frustrated that we have to recharge our handphone and laptop so frequently. Wouldn't it be good if we're able to charge these batteries less frequently, say once a week or once a month? That means that you basically have to have a material with much higher capacity. When we're looking at the two different types of material, first we have the cathode. It operates at a fairly high operating voltage, and then the anode operates at a lower operating voltage. For these two types of material, there are various different challenges. Let me, for example, share with you what we are trying to do with the anode material. Here, we would like to use a new material like silica to replace graphite. Why silica? Silica basically is a main component in sand. It is very inexpensive and very abundant. It also has a very high theoretical capacity, about 7 times higher than the currently used graphite materials. Now, the challenge, however, is that a lot of this material, they have fairly low ionic diffusivity. Also, they suffer from volume change when the lithium moves in and out of the structure of the material. To prevent these two problems, we basically want to make use of nanomaterials. Nanomaterial basically has a much shorter diffusion length and will lead to less, hopefully, volume change in the material. Now, to have better electronic conductivity, we are going to make use of a nanocomposite. Okay? First, to create a nanometer-sized material with walls of about 15 nanometers. Okay? What we would like to do is to use a template synthesis. Here, we start out with a manganese carbonate nanocube as a template. We coat it with silica, and then we remove the internal part, which is a manganese carbonate. We left behind basically cages like this, and you can see that I'm not exaggerating. Here we're really talking about nano walls. Okay, this nano walls is about 15 to 20 nanometers. Now, if we improve it by introducing a carbon, notice the capacity is slightly increased, but it is still falls short from its theoretical capacity. When we introduce another nanostructure material called graphene oxide, this graphene oxide will nicely wrap around our silica nanocage, and now our capacity is far higher than even the theoretical capacity of silica alone. We boost it to 2,700 mAh per gram. So this gives you a sense what we can do with the future of developing new energy storage materials. Okay? Allow me then to also share with you some of the recent breakthroughs we have in nanomedicine. Typically, we make use of carrier materials to deliver drugs. These carrier materials are made of polymers. They slowly hydrolyze and then release the drug in the process. In other words, it has no therapeutic effect, and you want to minimize the usage of such a material. What we will ultimately like to do is to create a material that will allow us to target the drug to the organ, for example, to the cancerous tumor. And also, at the same time, we want to create a carrier material that has therapeutic effect at the same time. For example, in East Asia, a lot of people like to drink green tea. Green tea has this component called catechin, or EGCG. This material is antibacterial, anti-cancer, and antioxidant. We want to formulate such a material into a nanocomplex, first by creating an oligomer. An oligomer basically has several units of this green tea catechin. We will be used to bind with the therapeutic protein. And then the exterior part of the nanoparticle is made of EGCG with a polyethylene glycol. What this polyethylene glycol does is basically it allows us to create a nanometer-sized particle that will be in circulation inside our body for extended period of time. It will prevent it from very fast clearance through the kidney. So with this nanoparticle, the key advantage we have now is that it will protect the therapeutic proteins from proteolysis, and it also allows us to make use of its very tiny particle size to attack the leaky vasculature in the tumor. So this allows us to have a passive targeting effect. By using such a technology, we can introduce therapeutic protein such as Herceptin, which is used to treat very commonly breast cancer. So in this case, we can see if you don't treat the cancer that is grafted into the mice, it will grow 5 times as large within just 1 month. This is shown in light blue. If you use Herceptin on its own, shown in yellow, you see that the tumor size will grow only 3 times instead of 5 times. Now, the remarkable effect is when you introduce Herceptin with this green tea nanocomplex shown in red, instead of growing the tumor, you actually shrink the tumor somewhat. So we have a major therapeutic effect through the synergism between the green tea and this therapeutic protein. Why does it work so well? If you have the protein by itself, which is shown in gray, notice how the Herceptin not only goes to the tumor, it goes to the kidney and the liver. It has a lot of horrible side effects. On the other hand, if you use the green tea with the micelle complex shown in green, notice how it gets delivered only mainly to the tumor. Okay? So it minimizes the side effect, and we can use this to deliver small molecule drugs such as sunitinib instead of just therapeutic proteins. Sunitinib is one of the few drugs that works for kidney cancer. It is very expensive and has to be administered daily, so it is very painful and has horrible side effects. What we're able to do here, shown in black, is that we are able to achieve better therapeutic effect with our green tea complex compared to sunitinib by itself, which is shown in red, and we were able to achieve this better therapeutic effect by using a lower dosage, okay? 7 instead of 60 milligram per kilogram, and less frequently, twice per week instead of daily. What this will mean is that you can save the cost dramatically, and most importantly, you don't have to administer daily, and you will have minimal side effects. Okay? Now, moving on, we want to not only make use of nanotechnology for medical treatment, we want to use it for rapid diagnosis. And one of the main issues with rapid diagnosis is that we have so many diseases, including infectious diseases, that people are suffering from. For example, dengue is the major cause of illness in the tropics and subtropics. Do you know that there are 400 million infections every year, and yet there is no vaccine? Okay? So be able to have a rapid diagnosis that is inexpensive will be key. Here, what I'm showing you is what is called a lateral flow immunoassay. Many of you probably are very familiar with this. This is a paper-based assay used in pregnancy tests. You can easily buy it from pharmacy and do the test quickly. The key here is you make use of nanoparticles so you can visually see the results. Okay? What we would like to do is to use this type of concept, but apply it to not just urine, but for, in this case, dengue, we need blood, or better still, we need saliva. Using saliva is going to be a major breakthrough because you don't need to prick your fingertips, it is non-invasive. But the challenge here is that saliva contains a lot of proteinaceous substances, and they really interfere with the detection process. To overcome this, what we have done is to basically try to separate the sample introduction and reagent into 2 different paths. They go through the reagent pad and the sample pad separately, and we have a regulator in between them that basically separates the 2 flows and bring them together. In this way, we can introduce the sample through the sample pad, remove all the proteinaceous substances before it meets the nanoparticles in the reagent path. By using this approach, we were able to achieve uniform flow, which is what is shown in the first graph. And most importantly, instead of this smudging and bad background that you would typically get from the lateral flow, we were able to get very clean signal, which is illustrated in the next graph. We were able to successfully detect the presence of dengue IgG in saliva in a matter of just 20 minutes. We're very excited about this breakthrough because it's the first time that we're able to use saliva to successfully detect dengue. Now, this paper-based diagnostic can be used for looking at different kinds of samples and can go beyond infectious diseases. We can basically detect a variety of proteins and small molecules. It can also be used for detecting nucleic acids. For example, we care about food safety, meat speciation, as well as GMO identification and pet diseases. Here, we basically can use a simple paper test, like a litmus test, to find out genetic testing to identify the DNA sequences in just a matter of minutes. There are also a lot of other technologies that we are very interested in. For example, cell culture technology is critical in industrial biotech. Here, we're talking about being able to produce therapeutic proteins, gene therapy, tissue engineering. And the scalability of these processes basically is constrained by the fact that they are unlike chemicals. They're very difficult to scale up and very difficult to monitor. Okay? So we would like to be able to monitor various different cellular health signals. For example, cell metabolism, cell identity, and cell viability. Okay. Currently, these are being done with very expensive kits in the laboratory. So for example, if we look at cell metabolism, they will require a 96 well plates, and also readers like a plate reader, which costs quite a lot of money. We are talking about multi-step operation involving incubation, and this typically takes 6-hour turnaround time. So it is way too slow for doing stream monitoring. What we would like to do is, again, using the technology that I described earlier, basically using paper strips that will allow you to test whether the cell metabolism is still good, and this has been done for the very first time now. We can basically do it in one step without the use of any equipment. It is simple. It requires just 5 minutes instead of 6 hours, okay? And you basically can save a lot of money in using these simple paper strips instead of well plates, and saving lots of costs because of miniaturization with this nanotechnology. In addition to monitoring, we are interested in cell culture substrates. Cell culture substrates that people currently use are things such as matrix gel, shown here. This is expensive, and it comes from an animal source. That means that it has variability from batch to batch, and it also has immunogenic issues. When people start using synthetic materials such as corning, this Syntamax material is basically peptides. It is very expensive. It's actually 10 times more expensive than matrix gel. What we would like to do is to create a nanotechnology that will allow us to easily coat cell culture plates, and this will be biocompatible material, non-immunogenic, pathogen-free, and inexpensive. We're talking about less than 10 cents for each well plate. Okay? So in this technology, we first chose the correct composition that will allow the cells to attach to these particles. But these particles can be easily can be easily turned into a suspension, sonicated, and coated onto well plates. And the key is we're able to maintain the stemness of the stem cell that will culture on this, and more importantly, shown here, after 25 passages, basically, most of the stem cells will lose its stemness, including, for example, using Syntamax. You see, it only maintains about 60 to 70% of the pluripotency, where else our material was able to maintain 98, 99% of the pluripotency. This is even better than matrix gel, the conventional material, which has animal origin, and ours is completely synthetic and much less expensive. Okay? So I don't think I have time to go into the nanotoxicology, because Klaus is coming towards me. So let me wrap it up by saying that I'm very grateful to be here. I hope to have shared with you some of the breakthroughs that we're able to make in nanotechnology for energy storage and also for medical technologies. Thank you very much for attention. Thank you very much.